Hey, all you ANML engineers out there, ready for a deep dive into YOLO. You only look once. I know as neural network experts, you already know all about it, but we're going deep today.
Okay.
Real-time object detection, it's a game changer.
Oh, for sure.
We've got a stack of research papers.
Okay.
All about YOLO, from the original paper to even a recent review that digs into how it's evolved.
Right.
And even looks at some of its surprising applications, especially in agriculture. So get ready for some serious aha moments.
Yeah, you know what's really fascinating is that YOLO came about when real-time object detection was like a huge bottleneck. Like existing methods, think RCNN, they were slow, computationally expensive because they needed multiple stages to process an image. And YOLO's like big innovation was that single stage approach. Analyze the whole image at once. Yeah. And it makes it super fast.
Before YOLO, if you wanted accuracy,
yeah,
you had to sacrifice speed. You could only have one or the other, but not both. And that's what was so groundbreaking about YOLO.
Exactly. The original YOLO paper, way back in 2015, 45 frames per second processing speed.
Wow.
Like, it just blew everything else out of the water.
Huge.
And it wasn't just speed. YOLO's ability to like, understand the whole image context meant fewer errors, you know? Especially those annoying background misclassifications that always mess things up before.
Oh, yeah. Okay, so let's get into the nitty-gritty. How does this single-stage magic actually work?
Yeah.
And I know our listeners, you neural network experts are going to want the details.
Of course.
So OG YOLO, it divides the image into a grid.
Right.
Each cell in that grid's job is to predict the bounding boxes around objects and then give probabilities to the different classes.
Yes.
It's like each cell is saying, hey, I'm 80% sure that's a dog, but maybe 20% it's a cat.
Yeah, like exactly. And then to make its predictions even better, YOLO uses a confidence score. Okay. That combines the object probability with what's called IOU, intersection over union.
Okay.
Which basically measures how well the predicted bounding box overlaps with the actual object.
So a high IOU, that means the model's really nailing the location.
Yeah, exactly. It's not just guessing it's in the general area. It's like right there.
That's it.
So a high confidence score means accurate classification and precise localization.
A powerful combo.
Right. Powerful combination.
But YOLO 1, like any new tech, had its limitations.
Yeah, it did.
And I bet those limitations were what fueled
the
rapid evolution of YOLO, right?
Yes.
Over the next several versions. It's like the developers are like, okay, we've got this awesome foundation.
Yeah.
How can we refine it? Let's push the boundary.
Absolutely. One of the first challenges was locating small objects.
Okay.
And dealing with groups of objects all clustered together.
Makes sense.
So YOLO 2 tackled that head on by introducing anchor boxes, which are like predefined shapes that act as references for the model. They kind of guide it towards better object localization.
Gotcha. So instead of the model starting from scratch every time,
it's
got those anchor boxes to use as the starting point.
Right.
Makes things more efficient, more precise.
Exactly. And to make things even better, YOLO 2 used batch normalization.
Oh, yeah.
Which helps stabilize training.
Yeah.
Leads to faster convergence, better overall accuracy.
Now, this is interesting for all our ML engineers listening.
Right. Yeah.
Batch normalization, it isn't limited to object detection.
Exactly.
It's used all over deep learning.
Yeah.
And seeing how it was used in YOLO 2, it's a great example of how you can take these fundamental concepts and adapt them to very specific tasks.
Absolutely.
But they didn't stop there.
No.
YOLO 3 came along.
Yes.
Took things even further. Introduced DarkNet 53.
Yes.
Deeper, more complex network.
Oh, yeah.
Way more complex than the previous versions.
Yeah.
It let the model learn way more intricate features, leading to even better accuracy.
Yes.
Deeper networks usually mean better performance.
Right.
But they also mean slower processing.
Yeah.
How did they keep that speed advantage?
That's where the brilliance comes in.
Okay.
YOLO v3 used something called multi-scale predictions. Basically, making predictions at different levels of detail to better detect objects of different sizes.
It's like having multiple sets of eyes.
Exactly.
Each one focusing on a different scale, so nothing gets missed.
Nothing slips through the cracks.
Clever.
It is clever. And then to deal with the complexity of classifying things
Okay.
into multiple categories.
They used binary cross-entropy for multi-label classification.
Yes.
Which makes training way easier, especially when you've got data sets with overlapping categories.
Exactly.
So again, it's not just about making the network bigger. It's about choosing the right techniques
Exactly.
for those specific challenges while still keeping that speed and accuracy.
Yeah.
And I bet that trend continues in later versions.
It does.
Right.
YOLO 4 was all about efficiency
Okay.
and performance. They brought in CSP DarkNet 53,
What?
like a supercharged DarkNet 53,
Okay.
to optimize that information flow within the network.
So not just deeper, but smarter.
Yeah.
Streamlining communication within the model.
Exactly. And then on top of that,
Mm-hmm.
SPP, spatial pyramid pooling.
Okay.
That helps the network understand objects at different scales.
Mm-hmm.
And PNET,
Okay.
a way to aggregate features so the model can pull out even more meaningful info from the images.
Sounds like YOLO 4 was a big leap,
Oh, it was huge.
on architecture and training.
And then YOLO 5, things changed again.
Okay.
This was the first version to use PyTorch, a much more widely used framework for DarkNet.
Oh, yeah. For AM engineers, this was huge.
Huge for accessibility.
Yeah.
I mean, PyTorch is like what everyone uses.
Right.
So this made YOLO accessible to way more people.
And it paved the way for faster development,
Right.
broader adoption.
Absolutely.
So what innovations did YOLO 5 bring?
Well, they introduced the focus structure.
Okay.
It's a clever way to downsample that input image without losing important info.
Okay.
So the model gets a quick but detailed overview
Okay.
before doing the deep analysis.
Like reading a book summary first
Exactly.
before diving into the chapters.
Exactly. You get the main points and then you go deeper.
Love that analogy. So we've covered the main innovations up to YOLO 5. I'm feeling those aha moments already.
Good.
But this is only the beginning.
Yeah.
In part 2, we'll look at those super advanced versions.
Yeah.
We'll explore those cool agricultural applications. And we'll uncover some surprising challenges and opportunities.
Yeah.
So stay tuned.
I can't wait. It's amazing, how evolution of YOLO really reflects the progress of deep learning, deeper networks, more efficient architectures, the move to more accessible frameworks.
Yeah.
It's all there in YOLO's journey.
It really shows how fast this field's moving.
Yeah.
And YOLO's been at the forefront, pushing the boundaries. But let's not get too lost in the tech stuff.
Right.
Our listeners, I think they're eager to hear about
Of course.
real-world applications.
Yeah.
So those agricultural applications.
Absolutely.
This is where YOLO really shines.
It does. The review paper,
Yeah.
it highlights all sorts of applications. Weed detection, crop classification, disease ID, even animal tracking.
Wow.
It just shows how a technology originally designed for general object detection can be fine-tuned to meet very specific needs.
And for our AML engineers out there,
Yeah.
this is where the inspiration comes in.
Absolutely.
Seeing YOLO used in agriculture might give them ideas for other industries.
Right.
Maybe even lead to totally new innovations.
Exactly. Let's look at some examples.
Okay.
One study, they used YOLO 3 Tiny,
Okay.
a lighter, faster version of YOLO 3 for real-time goosegrass detection
Okay.
in strawberry fields.
Now that one really caught my eye too.
Yeah.
As AML engineers, we all know model size, efficiency, it's super important.
It is.
Especially for real-time applications out in the field.
Yeah.
So seeing how they optimized YOLO for this,
Yeah.
it's really insightful.
They achieved really impressive accuracy in distinguishing between strawberry plants, goosegrass, and other weed species. And this precision is essential for targeted weed control. Lets farmers use less herbicide, reduce their environmental impact.
A perfect example of how AML can be used for sustainable agriculture. Precision spraying, guided by real-time object detection.
Would totally change the game.
It could.
For reducing chemical use and promoting eco-friendly farming practices.
Absolutely. And it goes beyond just weed control.
Okay.
Another study used YOLO 4 for something totally different. Detecting and tracking red foxes.
Okay.
They could monitor the foxes' movements and even analyze their behavior patterns.
Now that's thinking outside the box.
It is.
Shows how versatile YOLO is.
Yeah.
From detecting weeds to tracking wildlife.
Yeah.
All with the same tech.
Right. And this kind of wildlife monitoring
Yeah.
is crucial for conservation.
Right.
By understanding animal movements and behaviors, researchers can come up with better strategies to protect endangered species,
Okay.
manage ecosystems.
It's amazing to see how
Yeah.
YOLO is bridging the gap between tech
Right.
ecology. And it's not just limited to developed countries.
Yeah.
The review paper mentions a study in Bangladesh. Okay.
That used YOLO 7 to identify tea leaf diseases.
That's a great example of how YOLO can democratize access to advanced AML tech.
Yeah.
They used a Raspberry Pi,
Okay.
low cost,
Yeah.
easily available, accessible to farmers in developing countries where resources are limited.
Incredible.
Yeah.
It shows you don't need the most powerful hardware
Right.
to implement these solutions.
Exactly.
It's about balance.
Yeah.
Accuracy, efficiency, accessibility.
Precisely. And it opens up so many possibilities for using AML to solve problems in developing countries, from boosting agricultural productivity to improving healthcare and education.
Okay, so we've seen the potential of YOLO in agriculture.
We have.
But no tech is perfect, right? What are some challenges that researchers and developers face when deploying YOLO in the field?
One big challenge is data specificity.
Okay.
Deep learning models. They're only as good as the data they're trained on.
Makes sense.
So a model trained on, say, apple trees in one region might not do so well identifying diseases in apple trees in a different region.
Okay.
Different conditions, different varieties. It can all make a difference.
Classic problem
It is.
of generalization.
Yeah.
Like a self-driving car.
Right.
Trained in California. Might not do great in snowy Boston.
Exactly.
And this is where AML engineers come in.
Okay.
We need strategies to make these models more robust, more adaptable.
So, techniques like transfer learning, where you take a model pre-trained on a large, diverse data set and then fine-tune it on a smaller, more specific one.
Exactly. Like giving it a head start. It has the foundation. Then you specialize it.
Right. And then there's data augmentation.
Right. You create variations of the existing data to artificially increase the size and diversity of the training set.
So you're teaching the model to be more flexible, more adaptable.
Exactly. Then there's the Lauterfoger's hardware limitations.
Right.
Deploying YOLO on resource-constrained devices.
Yeah.
Like those Raspberry Pis can be tough.
Makes sense.
We need models that are lightweight, but still accurate.
That's always the challenge, right?
It is.
In AML, balancing performance and efficiency.
Luckily, there are techniques for that, too.
Okay.
Quantization reduces the precision of the model's weights and activations.
Okay.
Makes the model smaller. Uses less memory.
Like compressing the model, making it leaner.
Exactly. And then pruning. Removing unnecessary connections or neurons.
Simplifies the model. Reduces computational demand.
Like trimming the fat.
Right. And these techniques, combined with clever design and efficient training methods, they're pushing the limits.
It's really inspiring to see how AML engineers are tackling these challenges, coming up with solutions to make these powerful technologies accessible, practical for real-world use. But there's one challenge we haven't talked about yet.
Okay.
Maybe the most crucial one. Explainability.
You're right. That is key.
It is.
Especially when it comes to real-world applications like agriculture. Farmers need to trust the tech.
They do.
Understand why a model makes a prediction.
Absolutely.
Not just blindly accept the output.
Right. Imagine a farmer using a YOLO model to detect disease in their crops. If the model says, this plant is diseased, the farmer needs to know why before they do anything.
Like, what features is the model seeing? What patterns to make good decisions about treatment?
We can't just have these models be black boxes. We need to see inside. Make them transparent, understandable. So how do we do that?
That's a great question. And that's what we'll dig into in part 3 of our deep dive.
Stay tuned, folks. The best is yet to come. Welcome back for the final part of our YOLO deep dive.
Yes.
We've covered a lot,
We have.
from the technical details of how YOLO works to those amazing applications out there,
Yeah,
especially in agriculture.
absolutely.
But before we wrap up,
Yeah.
I want to circle back to something really important:
Okay.
explainability.
Right.
For AML engineers,
Yeah.
it's not enough to just build models that work.
Yeah.
We need to build models we understand,
Yeah.
models we can trust,
Absolutely.
especially when those models are making decisions that affect the real world.
It's crucial, especially in agriculture.
Where the model's output has real consequences
Right.
for farmers, consumers, the environment.
We can't just have these black boxes.
Well,
We need to make these AML tools more transparent,
yeah.
more accountable.
Okay.
So let's talk specifics.
Okay.
What techniques are AML engineers using to make YOLO and other deep learning models
Right.
more explainable?
Okay. Well, one promising area is
Yeah.
attention mechanisms.
Okay.
They've become really popular in deep learning,
Yeah.
and they basically allow us to see what parts of the input the model is focusing on
Right.
when making its prediction.
So instead of just getting a label like, this plant is diseased,
Exactly.
you can see a heat map
Right.
showing which parts of the plant the model looked at to make that decision.
Exactly. It's not just trusting the output.
Right.
It's about understanding the reasoning.
Okay, cool. What else? There are some techniques
Yeah.
from the field of interpretable machine learning
Yeah.
that can be really powerful.
Yeah.
Things like rule extraction and decision tree approximation.
Interesting. How do those work?
Well, the goal is
Yeah.
to take that complex decision-making process
Yeah.
of a neural network and distill it
Right.
into something more human-readable.
Okay, it makes sense.
So with rule extraction, we try to pull out a set of rules that the model seems to be following.
So we're reverse engineering the logic.
Exactly. Like uncovering the if-then statements
Right.
driving the predictions.
So it might be something like, if there's a brown spot
Exactly.
with this shape and this texture, then the plant's probably diseased.
Yes. And decision tree approximation
Okay.
is about creating a simplified decision tree
Right.
that imitates the deep learning model.
Okay.
And decision trees, they're much easier for us to understand than this web of neurons in a deep network.
Like creating a user-friendly interface
Exactly.
for the model's logic.
We can see how it's making decisions.
This is all fascinating.
Yeah.
But can we go even further?
What do you mean?
Can we understand how the model sees a concept
Okay.
as a whole?
That's a great question.
Yeah.
And that's where explainable AI is going.
Yeah.
One exciting area is
Yeah.
understanding the model's internal representations. It's about visualizing
Yeah.
and analyzing how the model encodes different concepts or categories within its layers.
So instead of, why did it classify this as a cat?
Exactly.
It's how does it represent cat?
What features,
Yeah.
what patterns does it associate with that category?
Wow.
It's like looking into the model's brain.
Amazing.
Yeah.
And this level of understanding
Yeah.
is key for trust,
Absolutely.
especially for real-world applications.
The more we understand,
Right.
the better we can use them responsibly.
Ethically.
Exactly.
So as we wrap up
Yeah.
our deep dive into YOLO, what's the main thing you want our listeners to take away?
Well, YOLO has been revolutionary.
It has.
Its impact is huge across many fields, especially agriculture. But as AML engineers, we can't just build powerful models.
Right.
We need to build models we understand. Explainability, it's not optional.
It's not.
It's essential
Right.
for responsible, ethical AI.
It's not just about making predictions.
Yeah.
It's about building truly intelligent systems
Yeah,
that we can work with and learn from.
absolutely.
And on that note, I think it's time to wrap up.
Okay.
Thanks for joining us
It's been a pleasure.
on this deep dive into the world of YOLO.
See you next time.